And welcome back. Now let's talk about the ways that a program gets run by a computer. There's two main ways, compilation or interpretation. Let's actually take a deeper dive into that. So compilation is the way C works, and the idea of that is you've got raw C code, okay? A compiler is a program that drinks in a C program and outputs something that's architecture specific. From the higher order, something that's local to that particular architecture. Different architectures. Back in the day, it was Mac versus PC, but even then, Apple decided to change the underlying CPU and the underlying instruction set architecture they used to actually be an Intel one, and then if actually the differences weren't that much at all, and Apple is now recently, this won't be recent if this is a video, as of 2020, I'll say, Apple is changing their architecture to be an ARM processor. So it'll actually be a different instruction set architecture. They're going to make their own chips. And as a result of that, you're going to see different architectures now for PCs and Macs again. So we went different to the same to different again. Java, what Java does is it compiles it down as well. Remember, Java C is Java compiler. If you remember what the C in Java C means, it's Java compiler. And it compiles it down to this something called architecture independence. And that was a big deal. Because C, you lock it into the particular architecture it builds on. You're going to build it for, you port it to a machine and you build it for an architecture. I can't just take the executable and run it on a different architecture. In Java, you can. This portable bytecode is something you can now pass around to different machines and just run that. And then there's an interpreter that interprets the bytecode. So actually, Java has both, a compiler and an interpreter, allowing you to have machine-independent code, which is actually pretty powerful. Python does this real, runtime bytecode conversion, but Python is mostly interpret. You can think of it as being interpreted. It does this bytecode conversion in runtime. In C, there's actually a two-step, there's a picture and a slide or two. There's a two-step process. You first compile it down to .o files. This is the compiling it down to the assembler language. And then you link those with libraries to form the executable. So it's really a two-step process, but it's hidden because you just type GCC and it makes executable. So you're kind of missing those two steps. Assembling is done, but it's often, as I said, done automatically. There's the picture I was talking about. So I've got two programs, foo.c and bar.c. They both are run through a compiler. And I decided to just highlight foo.c in bold. Let's say I just made a change to that one. The reason I highlighted it, I wanted to show you this. You then compile them both down. Now you've got this machine code, object file, .o file. We call them .o files. It's machine code, object files. Now I've got to put that together as an executable. So you can't just run a .o file. You have to then link it together with whatever libraries are needed. You link them together at runtime, not runtime, at linking time, not at runtime, at linking time, to build a.out or the actual executable that you can now run. So I can run that there. The reason I highlight foo.c, watch what happens if I were to change only foo.c. Well, what happens? Do I need to compile bar.c? Look at that. You're like, no, you already have bar.o. Bar didn't change. Bar.c didn't change, and bar.o doesn't need to be recompiled. That's one of the big ideas of what makefiles do for you. So if I only change one file, it only follows it down. Do I have to relink it? Yes, I still have to relink it together. But the idea, I could have bar.c and a million other programs. None of them have to be compiled together. Those .o's are all done, and now I can then link them all together with whatever libraries. So it's kind of fast. So it's not as bad if I make a small one-line change, I compile that one file and then link everybody else's .o with the new .o I just created to make the executable. Advantage of compilation. We've worked with makefiles. I kind of talked about that a second ago. We work with makefiles, so you only need to actually recompile the things you've changed. That's a big deal. That's nice. That's, by the way, another reason to segment your code into different files. If you all have it in one gargantuan file and you make a change, you have to then compile the entire thing down. It's much more efficient to just have a lot of small files. It's also better for management as this thing grows. That's why Java encourages lots of classes, different file names, so that you only have to worry about the one that you've changed. That's really great. Runtime performance is unparalleled. You're never going to see anything run faster than C. Assembler is essentially the same thing as C. C compiles down to raw assembler. But compiled languages in general are as fast as it gets. There's no stages of needing to read the source code again and reinterpret it at runtime. You've already got the machine code, you're just doing it. It's raw silicon. It's great. I mean, run on raw silicon, which is exciting. Now, you say that, but Dan, people still do lots of big data processing in Python. Here's the reason. Because a lot of libraries have been optimized for some hardware. So GPUs, we're going to learn about GPUs in this class, graphics processing units, are now general purpose. For a while, they were calling them GP GPUs, general purpose GPUs. Before, in the early days, their job was to take polygons and render them into pixels. Now they're general purpose, and so you can speed up your Photoshop, you can speed up lots of computation, and from Python, by calling libraries that know how to harness the GPU, which is great. GPU is amazing, waiting to be tapped as a resource for you. So Python is still used because a lot of libraries optimize and use the GPU. Also, Spark is a way very easily in Python to kind of, as a director, as a marionette controller, control lots of other machines. Millions of machines can wake up and do your bidding, and driven from Python, which is really fun and easy to program in, I'll admit, so that's great. Also, you can make a connection, write C code, and expose it to Python. So in Python, you can be calling the C program. So that's called Cython, and you can check out cython.org, I believe is the website. So you can also have the best of both worlds, where you're living in Python up here, but when you need some actual, lots of work done, lots of spinning in a loop, doing something fast, that needs to be as fast as possible. Well, that actually could be C code doing the actual work of that's compiled up and then called from Python. So that's pretty cool. Disadvantages. Well, the compile, the touch a file, compile, link, run, find the error, back to compile. That's a slower process than just interpreting or sitting in a REPL, sitting in a read, evaluate, print loop. It's much more fun and easy to kind of have a snippet of code, just pipe it there. You can't really have a snippet. It's not really a C interpreter. Some folks have tried that. I actually had one at some point, but that's not really a thing that most people have who are C programmers. So it's hard to just have a little line of C code that you want to see what it does, just to see, does that really move the bits in this way? Well, not really. You have to actually go and make a program and make a little print thing to test that. So it's a little easier to live in an interpreter. So the disadvantage is compiled files, because you don't have an interpreter to play with things, is not so good. Also, compiled files, as the first bullet says, are machine specific. So the .o files and the executable are machine specific, which means you have to then port it when you move it to another system or another operating system. You'll say, but Dan, wait, Windows and Mac back in the day when they're both x86, that's the same, same CPU, doesn't it work? No, because the libraries aren't the same. So all these things have to work in the same ecosystem cleanly, even though the actual underlying CPU is fine. It's the same. So the idea of recompiling and moving it to another architecture is called porting your code. And that's always a pain because things are different. Oh, is it big Endian or little Endian? You'll learn what that means later in this class. What's the size of an int? In fact, if you ever type configure, it'll show you about a couple hundred things it's asking you about that particular system, and they're often different. Even a different system might have a different library, or a different version of the OS might have different versions of this. Oh, we're now 64-bit ints versus 32-bit ints. These things are all independent, and all those things lock in. Once you lock in an executable, it locks in that pattern. It won't run if any of those things are changed, and that's really hard sometimes. So again, I mentioned the change, compile, repeat is slower than it is. The nice thing, by the way, I mentioned that you'd only have to compile the particular file that you've changed. They've also come up with a parallel compiler. If you type make -j, you can imagine the parallelization possibilities. If I have 100 files, never been compiled before, I can compile them all in parallel. If I have a machine with 100 different cores and I can be accessing my SSD really fast, I could actually be very efficient with that. So they all happen at once, the compile stage, and then the linking together is still that, that's the bottleneck. You're going to see the Amdahl's heartbreaking law, where you have to go through a bottleneck that's a serial part of it, and you all have to wait. I'm sorry that you were fast in parallel, but I still have to go through this linking bottleneck for that. You'll see that when we talk about Amdahl's law, but just know that a bottleneck is really going to be hard to make that much faster. There is the availability of a C preprocessor. What that means is it's something that takes the C code you've written that might have some directives, have some things that are special, only commands for the C preprocessor that can kind of processed and then release into a .i file, and this .i file is then what the compiler sees. So it's actually quite interesting. So anything that starts with a hashtag, a pound sign, is a C preprocessor command. So #include is the way that you include a header file into that, and actually grabs the header and drops it right in. It doesn't just point a link to it, it's not a reference to it, it literally grabs the .h file and puts it in to the .i file. It actually just inserts it in. Standard IO.h is the same thing, but when you have the angle brackets, it does the same thing, but the idea is it's saying it's grabbing from the standard place in the library. You have to have a special where the include files in your path for that, but it looks for the standard place for standard libraries like that. You can pound define globals. Here I'm defining pi to be some number. Typically, you put parentheses around them because you never know where that's going to be in an expression. So just wrap things in parentheses when you have a pound define just to be safe. There's also if-def, if and if-def, and end-if. And that's a way to kind of say this code will only run if this is defined before, or if this has been seen, or this variable is true, some expression is true. So this means only run this. It's actually quite clever. You can kind of do debugging by wrapping your stuff, by having a debug flag that goes true or false, and then it won't print out anything by just recompiling with the debug flag true or false. It's kind of a nice thing. The full documentation for the C preprocessor is at the bottom line as well. If you type -save temps to GCC, it'll actually save the files. So you'll actually see the process and actually save the .i files in your directory. So if you want to actually see what does that .i file look like, take a look at it and say, call save temps. There's a warning. The C preprocessor is great. One of the things you can do is you can pound define macros. Macros are really great for kind of making fast code, but it can also make code that's hard to debug. So let's talk about that. So what happens is you're making this macro that text replaces everything it sees below. It's not like it's calling the macro, it just text replaces it. So if I said pound define min of xy to be, remember, we wrap parentheses around these guys just so that the kind of whatever expression gets evaluated first. So you see this parens x less than parens y question mark, that's the ternary if that you see there. If that's true, then it's the x expression, otherwise it's the y expression. So that min seems very innocuous, right? Seems fine. And mostly works, except when one of the values of x and y happens to be a function call. That seems fine, except the function call has a side effect. Let's say print out hello world, okay? Let's just say. So foo_z has a side effect. And now I say next equals min. So now, by the way, I can call min just like I can call a function below. Once I've done this pound define a macro, I can call min just like the function. I say min w, I call to foo_z. And that's fine. Normally what would have happened is foo_z would have been called, prints hello world, and then says whatever, returns some value, and then the smaller of the value the foo and w returns is the value set to next. Seems innocuous, right? Except the idea that it does a substitution. So imagine taking all of the expressions w and replacing it in x, and all the expression foo_z replacing it in y. And what do you have now? 2 possible calls to foo_z. You understand? So now, is w less than foo_z? You got to call foo_z. Now it prints out hello world. And if, let's say it isn't, well, you're going to go to foo_z again, because foo_z was the bigger value, was the smaller value. Actually, it was smaller value, right? Is the bigger value. No, sorry, if it's the smaller value. We're looking for the min. If it's a smaller value, if foo happened to win the smaller value competition, then foo gets called again to return its value, and print hello world gets called twice. Very simple case, but you can imagine if you have any side effects in this very simple case of min. So be careful with macros is what the point of this slide was. So in general, this little mini lecture was about compilation versus interpretation and thinking about the powerful idea of a C preprocessor and how the whole thing works in terms of linking and compilation together. See you at the next lecture. Thanks.